Hey everyone, welcome back to our weekly episode of Hacking on the Raspberry Pi Pico emulator. I'm happy to see that we already have a few people here, and I would love if you say hi on the chat and let me know that the audio and everything is working as usual. And today I have a couple of news to share, so let me share my screen first. You should be now seeing my screen. So let's start with the most exciting part, for me at least. Which is this new course that Hackaday and I are going to do about the Raspberry Pi Pico, basically taking everything I learned in these sessions and packing it into a very intensive 5-session course about Raspberry Pi Pico, the RP2040, and basically everything we are doing here, but more from like learning perspective and less from creating an emulator perspective. So that's one thing, and it's starting next month, and I would really love to use the simulator for that. So in order for that to work, we need to make sure that the Raspberry Pi emulator will be ready in time. I hope it's a bit of a stretch to get it ready in time, but we will work hard, and I hope we'll get it to a usable state by then. On a different note, this Arduino core for Raspberry Pi, the official one, was released this week. I haven't looked into it too much, but it's basically based on Embed, which is some kind of SDK or something like that from ARM, and you can install it and start using it with Arduino to build code for the RP2040. And I guess we will get to that probably next time when we try to build Blink or something like that with the Arduino core and run it in our emulator. We have I have a little debt to you from last week. We released the first version of the library RP2040JS to NPM, and so there we did it, and we had like some issue with figuring out how to include both ES modules and CommonJS variations of the code in the same package. So I did some Googling, and I found a guide that was published just like 2 months ago. That should be pretty useful. But before we get into that, let's just hey Punith, thanks for the feedback on the chat. So before we get into that, let's just go and see what we were doing last time, because honestly I don't remember that good. So first of all, we have this emulator run. We released a version to NPM, and I think we started working on timers and wanted to get a low serial, which is different than a low UART that we used before. So we wanted to get that to work. Let's see. I think we got stuck, in some kind of panic, and then we figured out we would need to implement the panic. Loud and clear, panic. And then we figured out that we would need to get the timers to work, I think. So we started refactoring peripherals and worked on this timer. And probably then we had a few missing instructions. I guess they are, in the Git log. So we had those instructions that we wanted to implement because they were used in the code, and that I don't know where are those. I don't know if they are the reason for the panic. I guess it has to do with the timers. We can actually look for this piece of code. Attempted to sleep inside of an exception handler. How did we get to an exception handler? I don't think we implemented exception handling yet. Let's see that. Attempted to sleep. yeah, so this is the panic. I guess get current exception returns something that it shouldn't, and that's the reason why it gets into this if statement. But actually, if we are already here, let's take a look of how sleep until works. If it uses interrupts, or yeah, basically it uses busy wait. So maybe, oh, I see. It adds an alarm, and then WFE is wait for event. So it just waits until the some interrupt probably occurs, that of the alarm, but it also like checks the time. So maybe in this case we can even get away without implementing interrupts, but in order for this to work, we need to get current exception. We need this one to return 0, I guess, which means we are not in an exception. Yeah, and I see it uses this MRS instruction, which I think we haven't really implemented. I think we just have like this kind of placeholder. So that could probably be the reason why it gets this panic. And you can see like there is like this MRS probably here or here. One of those is where it's trying to load this IPSR, and things go wrong then. So let's try to fix that first, and then we can worry about the missing instructions. And after we fix that, I think after we we got hello serial to work, then we can probably make another release to npm. Cool. And hi, Tomasz and Valerio. Yeah, Valerio, or have you tried running this code on your own machine? Because you say you don't get a panic, it just gets stuck after the first loop waiting for WFE. So have you tried running it on your own machine? Okay. Anyway, we need to make sure that this one does something. Copies IPSR into R0, and let's take a look at what we have right now. MRS, right? Yeah, we just console log MRS. We don't even decode it. So yeah, let's start by decoding it, I guess. And let's go to the datasheet. And oh yeah, I remember we did this just so it's a two-word instruction, so it has like 32 bits. So we didn't want the second part of it to be interpreted as different instruction, and that's why we added this code just to to decode it and skip over it, but not execute it. So let's see, MRS, where are you, MRS? Cool. So we have RD and sysm, and then sysm is like 8 bits. So it's just can write it the same way it's written, opcode, so lower 8 bits, and then 1, 2, 3, 4 next bits are for the RD. RD is opcode, shifting it right 8 and taking 4 bits. Maybe this way. Yeah, it looks better. And let's, I guess, add a test case for that. So RP2040. You go there. RP2040 spec. Let's remove this, and we don't have like a test case for MRS yet, so MRS, yeah, it can come after moves. MRS R0 IPSR, and let's see what it decodes to. Probably we have it in one of those listing files, or maybe we don't. Isn't there any precompiled listing file with this instruction? I mean, we can probably run the emulator and set a breakpoint then, or we can just console log it, because it's executed right before. We can also console log rd and sysm. Right. Sesame, open sesame to string 16. Cool. And now let's run it and see the opcodes. And then we can, okay. So yeah, that's probably not the instruction we were looking for, because it should happen with R0, and here we have like R3, or we didn't decode correctly. Oh, yeah, I think we read from the wrong part. Let's see if that makes more sense. Still the same. Interesting. I wonder how we got 3 instead of 0. Now it's 3 and 16. Doesn't make a lot of sense either. Yeah, but obviously it should be read from opcode 2, because in opcode 1 we use all of the bits, and in opcode 2 we just use 4 bits. So that's the correct one. First bug spotted, but still we wait a second, something happened here. Oh yeah, that's we wanted the one that comes before the panic, I guess, somewhere. Yeah, 0 and 5. So yeah, that's probably the opcode we were looking at. So, and then that's the second opcode, and that's together MRS R, what was that, 0 and IPSR. We just need to double check that IPSR is indeed number 5, and then we expect R0 to equal, what is IPSR anyway? I think we implemented it. Yeah, it's basically 0 right now, because we haven't implemented any interrupt. So let's just check that it actually moves something. So we'll start with putting some other value in R0. Registers R0 equals 55, just for the sake of it. And then if this opcode is executed correctly, it should increment PC by 4, and also set R0 to IPSR, which is 0. And now we can implement it, but I just want to double check that IPSR is actually number 5, just to is there like any index that tell us the spatial register numbers? Yes, sysm value IPSR 5, perfect. So yeah, so we decoded this correctly. Cool, so we don't need those console logs, and now we can say this dot if sys, or maybe switch sysm. So in case it's 5, we can actually implement a few more, because we also have those registers. Yeah, and at some point we'll have others, but for now maybe we'll create a constant for this sysm IPSR. So for sysm IPSR, all right, yeah, so yeah, we have all of those. Okay, so sysm IPSR, then we can do these dot registers rd equals d dot IPSR, and we can already, I mean, we are already here. Test passes, by the way, which is cool. So we can implement a few more those registers that we already have, like IPSR is 0. And then we have system IPSR. So if it's IPSR, then do the same just with IPSR. And break, of course. And in the otherwise, console.log or warn even MRS with unknown register and the value of system, or maybe unimplemented system value. And while we are at it, we can also implement MRS, which I guess is just the opposite of MSR. But first, let's check if this fixed the issue in the code. Oh, we got somewhere else, I think, what happened here. It's definitely different. Let's just start it and stop it real quick. Yeah, so we can see the log. Oh, yeah. That's great. It prints a hello world, so it works. I think it did before. And then it writes to register number 16, primask, probably masking out some interrupts. Read from invalid memory address. What's there? D000. I think that's the SAO, if I'm not mistaken. Or maybe I'm just speaking nonsense. Yeah, SAO. So what's it? 140. 140. Spin lock. Oh, I remember those spin locks. Yeah. Why are we using them? Not sure. Anyway, it gets into this probably loop where we have an unimplemented instruction. Let's take a look there. Let's start it again with GDB. Do we execute run emulator? We run a GDB server, so let's GDB multi. No, GDB multi R. We need to find the L file. So that's inside Pico. Pico examples build. Serial UART, yeah, and then inside the it was inside the hello world, and then hello serial. That's the one, right? Serial. All right. GDB multi arc file that was hello serial.elf. Okay, target remote winhost 333, and let's start this one and see where we get stuck. Connecting where? To Micro's Sense boot. All right, interesting. Yeah, it's inside sleep waiting, and then we have this instruction. Why is it still running though? I thought we at a breakpoint. I mean, GDB interrupted it. Interesting. Anyway, we have this memory address EF0. That was we said 1000 EF0. This assembly/r EF00. Wait for event. Yeah. So I think this is like the busy wait we have seen before. This wait for event. What is it called? We are inside sleep until sleep micros. Yeah. Let's open that. Sleep until. The SK one probably is the better choice. yeah, it's the same function, and then I guess time is never reached, and that's why we have like this loop that waits for events until the time is reached. So first of all, let's just implement this WFE so we don't get all those problems, like all those logs, even though I'm wondering what is like the unit of t. Like it's a lot of microseconds to sleep. I think it's more than like, or maybe, yeah, I think it's sleeping for too long, like yeah, I know what's the problem is. So we are trying to sleep for 1 second, which is 1000 ms, but then the conversion to microsecond goes wrong, and then it just sleeps for too long. And the reason for that is that we are probably inside sleep ms, we are probably multiplying, obviously, and then we haven't implemented that yet. I think it was on our list to implement. Not this one, that was, where are we? Yeah, it was on our list to multiply two numbers, and we haven't done this yet. So let's do it now, and then it will sleep for an amount of time that does make sense. All right, so new instruction that was, actually, let's do all of them already. Cool. We know we'll need them, maybe sooner than later. Okay, so these are the instructions, and let's create. Let's start with the. Let's start with this one. With the, I think it's easier because we have another version of it, UXTB. Where is UXTH? Cool. So that's the encoding, and let's create assembler for it. Assembler stack here. Assembler goes there. All right, and cool. Where are we? Yeah, UXTB, and now we want another one. So we had not this one. Actually, let's keep it here. It's handy. Yeah, we had this one. So it should correctly encode UXTH, and then we expect R3 with R0 and UXTH to equal this. All right, and then now we need to implement this opcode UXTH, and just, you know, change the prefix. Otherwise, it's pretty much the same as UXTB. So, and yeah, auto imports always fail. We know that. I mean, sometimes they do, sometimes they don't. Anyway, now something is totally wrong here. I don't know what. I mean, just added an import. Why did? Okay, cool. Yeah. So R3 R0 expected received. Okay. Why is that? 3 bits, RD, RM. Seems legit. What did I miss here? Oh, UXTH. I think maybe the byte. Yeah, the byte order. Wonder why the byte order is different. Anyway, let's hope this works. I don't know why it was different. I don't remember we had to reverse them in the past, but I mean, it works, so probably it is correct. Okay, let's do the other opcodes as well now. So we'll be done with these files. And why is this red? What's wrong here? Oh, I need to close the parentheses. Okay, so we have also MULS. So let's add it right after move. We also already have like this encoding for MRS and MSR, but I will maybe change the test later to fix that. Let's first of all finish with this MULS R0 R2 should equal to 4350 maybe, and R0 R2 MULS, all right, 4350 coming from here, and then let's do, actually this should come below MRS and MSR. Okay, MRS, MSR. Okay, and now we have MULS with, I guess it's pretty similar to this one, so we can copy paste. Let's see, MULS. That was, yep. 3 bits, 3 bits, 3 bits, 3 bits, perfect. Cool. So now, cool, we have this MULS, just import it. Okay, output, oh, it's already green, perfect. So the test is passing, we already know that, we don't need to look for the test. And we have rev. Where do we put rev? Yeah, just between pop and RSBS. So rev R3 and R1 should equal to BA0B coming from here, and we encode opcode rev with R3 R1. Cool, let's do that opcode. Was just right after pop, and probably same as this one, rev, yep, and 3 bits and 3 bits. So yeah, so this is rev, just change the prefix. All right, and import it, and hopefully this will go green, and we'll be happy because we finished with the new opcodes. Yes, this is green, so the test passes, and we can move on to implementing the instructions. Cool. So let's do the tests as usual. First, P2040, and let's start with UXTH, just because we started with the UXTB. I mean, just before we started with it before, and R3, R1, whatever, doesn't really matter. UXTH, R3, R1, and then R1 is just like what is, the registers are equal. They're like, they're like, I think this is a copy paste mistakes. This is like, we copied it from here. Yeah, so just UXTH instruction, and also here, and maybe here it should be when the registers are equal. Yep. Okay, cool. All right, so we have this value, and then what does UX? I think it just removes the not word rev, UXTH unsigned extend half word. Yeah, extract 16-bit from a register and 0 extend it. So basically just removing this higher part of the value, so it should equal this. Cool, we have the first test case, but it just R3 should have the result, because that's the second register we pass here. So first test case is ready. Now let's implement this UXTH. So what is probably going to be pretty much copy paste from UXTB, UXTH, and then we can say we need to take the prefix, we have it here, and the decoding will be the same. All right, prefix decoding, and then just change the mask to be 16 bits, and it works. Green, perfect. Next instruction, MULS. That was after this MOV. Yeah. So so that would be MULS R0 R2 and opcode MULS R0 R2, and let's say that R0, so it multiplies. Let's make sure that it does what I think it does, but I think it does R0 by R2, multiplies them, and then unsigned int or signed it. Okay, it doesn't matter. It says they produce the same final result. I just multiply them and get the lower 32 bits. All right, so let's say this is like R0 is 5, and then R2 is like I don't know, 1 million. That wasn't 1 million, that's 1 million, and then we expect R0, right? RD. Huh? Oh, RDN, yeah. Yeah, I think it should save the result to MULS. First operand, destination register. RD can be omitted. Huh? Right. Anyway, I think it should save the result to RN, right? D is RDM. Or maybe not. Yeah, it seems like the result is written to the second operand, so to R2. So in this case, I expect R2 to equal 5 million, right? Let's just import it. R0, R2, all right, and then let's assert on the flags. So it's definitely not 0, and it's not negative, so they both should be false. Or I'm wondering if it doesn't make sense to me that it saves the. Yeah, it usually like saves the result to the first operand. So am I missing here something? Or is it like something spatial with MULS? Let's just check adds. How does adds work? RD, RN. Okay, I want RDN, one that has RDM. Let's. Yeah. And RN, yeah, this one. Oh, this is also, this is the, yeah, I guess. What's the difference between MULS and MULS? Interesting. Yeah, anyway, it seems like it's the only instruction with oh yeah, it's the same instruction. Perfect. It's the only instruction with RDM, so probably it's something specific to this instruction. Okay. All right, so let's implement it. That was. See that I have this like pattern here that I almost broke here with UXTH. All right, so move. Then after all of this, we have. Usually it's RDN, not RDM. That's strange. Anyway, let's implement MULS. And this is the prefix. Okay, perfect. Prefix and RM. No, now it's tricky. It's RN and RDM. Why? I don't know, but that's what they decided. And then the result is just like multiplying those two registers, Rn and Rdm, and then Rdm is equal to the result and 0, and okay, that sounds good. Just something doesn't work here because it didn't multiply those. The result was just copying of this value. It didn't do anything. Why is that? Oh, interesting. Maybe I think I know. Yeah, probably the encoding swapped the values, maybe. Let's double check the encoding. So we have Rn, it's called here, and Rdm. And then Rn is like the higher one, and Rdm is in the lower bits. Okay, so yeah, interesting. So now this test fails. I wonder if there is a mistake in the datasheet. This like Rdm, it doesn't seem to me, but you never know. Anyway, now the test passes, so something is wrong. Either this is like writing the registers the opposite way. Interesting. Let's take a look at how this is encoded. So we expect the lower 3 bits to have the destination register. In this case, it would be the second one, right? Wait a second, there is no RDN here. RDM, that's RM. So yeah, so we expect the second register value to be in the lower bits, and the second register value in this case, let's go back to the assembler spec file. Why do we have all those spaces here? Don't need so many empty lines. It doesn't serve any purpose. Thank you. Okay. Yeah. Now it doesn't encode correctly. So we expect, yeah, something is fishy about this instruction. Where is something fishy? Okay, MULS, RN, RD, RM. In RD and RD is RD. Yeah, it seems like MULS, the destination is the second one. Very strange. I feel like I'm missing something here. Maybe R0, that's Rn, 2, destination register. Again, so Rn, that's the first, I guess, operand. That should be here, and the first operand here is 0. So I expect this one to have the 0 and this one to have the 2. So something is not correct about this encoding. Yeah, I don't know. I guess I will just assume that the decompiler did something wrong, and this should be like that. I don't know. I hope it won't bite us. I have no other way to explain this, unless I'm missing something, and if so, please let me know. Maybe I'm blind to it. Anyway, so now MULS work, and we have rev which will hopefully be a bit easier than this. Oh, I wanted to add another test, or maybe and set the 0 that when the result is 0, just to make sure we are doing the right thing with the flag. So if we multiply this by 0, we expect the result to be 0 and this to be true. Huh? Oh, that's the negative, the end flag. 0 should be true. Cool. And let's another one. Let's have another one where we have yeah, and now let's make it negative. Let's say 1 or -1, and then this should equal -10,000 -1 million, but it should be signed, so convert it to signed. Now negative is true, 0 is false. End flag when the result is negative. Maybe I will just change it to Z flag. Cool. So MULS tested and worked, unless we messed up with the opcoding coding, which we'll find out very soon if we did. Hey Nekari, good to see you here. And what else? We have this rev instruction. So yeah, it's a mess. We should yeah, the ordering is a mess, I think. Not really ordered. Anyway, let's add this rev test for the rev instruction. Yeah, just before RSPS. So let's do rev R3 R1, and then we can copy this, and I think the rev doesn't touch the flags, if I remember correctly from last week. Should be pretty straightforward. It just reverses the byte order, so it should be pretty trivial to implement. So RM RD, and yeah, it stores the result in RD. So R2, whatever, and then R3, let's say, equals to 1 1 2 2 3 3 4 4, and then we expect after the instructions R2 to equal 4 4 3 3 2 2 1 1, just reversing the bytes. And let's implement it just below RSPS. So same decoding semantics as this RSPS, so rev, and we have this prefix, nice and long, right, cool, and RN, then RD, RM here, then RD. And what we want to do is just to say RD equals, and then we need to swap the bytes. So let's take the bytes and swap them. So first of all, the lower bytes, so const input is this.registers RM, yep. And then input and FF, and that's shifted by 24, so it becomes the high byte, and then we do pretty much the same, but then input shifted by 8, and this is shifted by 16. Then maybe we need extra parentheses. I never remember the operator precedence in this case. So 16 and 8, and finally 24, and we don't need to shift it. And no or, and then just format the code and let it figure out the parentheses. Okay, cool. And it doesn't work. Why doesn't it work? RB2040. registers are 2 to string 16. What do we get here? Huh? Where did we get these? ECCC, EEDDBCC. Why did we mess up here? Wait a second. It doesn't even get into this. Let's focus on this one. Oh yeah, it should be opcode rev. That's true. And now it's green. Perfect. So we didn't mess up anything, and we got a bunch of new instructions. Cool. Let's run the code. See that it doesn't complain about any missing instructions other than this wait for event, and then oh right, it's already running. Yep. And then we'll also implement wait for event, but let's see if it stopped complaining about. We can't see because there is too much output. Yeah. Oh, there was unimplemented something here. Yeah, so that's the only unimplemented instruction now, which is WFE. So just for the sake of you know, not getting a lot of errors, let's just simple. We are not going to implement it right now, just decode it so we don't get those warnings. So to be very last, else if opcode equals this specific value, do nothing for now. Just wait for an event, you know. All right, so now we should get rid of those reads. Okay, it didn't work. We still get oh, 0b, not 0x. That explains everything. Cool. But we still get those errors. Why is that? Interesting. Let's see. What's going on? 3F20, but that's BF20. Why do we have a different? Is there like another WFE or something like that? Oh, wait a second. There were two encodings? No, there is only one. Okay, interesting. All right. Hey, wait a second. Something is missing here. It's not the same. Yeah, that's a copy-paste mistake probably. Let's see if now it works. Yeah, okay, cool. So yeah, I think it works. Like we have a hello world, it delays for some time, probably a second, and then we have a hello world again. Let's just double check by setting a breakpoint in the GDB debugger so we can see that the multiplication was done correctly. That was file hello serial.elf maybe? No. Oh, SL is fun. I should actually install it. So just if you don't know SL for Unix, it's like when you have a typo in ls, you get a steam locomotive. Just a fun fact about Unix that some of you probably didn't know before. So next time you misspell ls, install this tool. It's fun. Anyway, so now I'll write ls correctly, and that was hello underscore serial. And let's also target remote Windows 333. Yes, thanks Che Guevara's for the feedback in the chat. I think it's fine. We'll know in a moment. Let's set a breakpoint, or where are we? We're probably in the delay anyway. Okay, so sleep micros seem correct like this. well, this is like 1000 times 1000. So let's just double check this sleep until. I think it's correct as well. I don't know how it's sleep US. So sleep until make timeout time US. Micros delayed by micros get absolute time, and this probably adds two numbers. Anyway, this multiplication works, and I think this is okay because we are getting like those hello world, hello world, hello world, hello world, probably every second, and a few reads from an unimplemented address, but that's fine. Cool. So good time to commit. All right, fit RP2040 implement, or maybe just what we implemented. We added MRS or MSR. I always forget. That was MRS, as well as MULS, as well as rev, as well as UXTH, also stub for WFE. And do we have any other interesting things here? Just a few imports. Yeah, I think we close this so we have a full view. Yeah, I think we just, what did we change here? Oh, yeah, for some reason it wasn't indented correctly, so probably this, I don't know how it came to be not indented correctly, because it has to be auto formatted on every commit. That's strange. Anyway, now it's formatted correctly. Test cases. Huh? Ooh, what is this? Think. Yeah, we probably forgot to change, or yeah, we probably mixed them up. This is the MRS one, and this is the moves. And since we are already here, we can probably change this to flash view, right? Unit 32 opcode MRS with R0 and 5, which is 5 IPSR, and that should be with true, and at position 0. And why isn't it happy? Not a function. Maybe set unit 32. Yeah. Okay, cool. And it's still green now, using the function that we wrote instead of this cryptic opcode, and still passes, which is cool. Okay. All right. So we reviewed this one. We reviewed this one. We we warned when we have an unknown register, so that's great. Okay, correctly, blah 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 blah. Seems legit. Let's commit and have some fun. Cool. So I think at this case, at this stage, we got hello serial sort of working. We have timers sort of implemented, still without interrupts. And this means that we can run hello serial, which is pretty cool. Let's solve that issue with the npm release, or try to fix that. There was like this guide that I found how to create it, how to create the package, and they have like all those introduction and issues, but then they have like the solution somewhere. Yeah, the solution. This is what we need. So they are doing something very similar, like compiling twice, and then they are also running a fix-up script, which we'll have a look at in a moment. And then one of their files is just compiling ESNext modules, and the other CommonJS, and a base file. and then there is a different package JSON. That's the fixup script. It creates a new package JSON in each dist directory. So I think we already have this setup where we have CJS and ESM, and that's probably what we missed last time, where we have we need a small package JSON in each of them to tell Node this is like CJS require and a CommonJS, and this is like ESM. And then inside the package JSON, they have these exports fields, and I think we had it, but they have like instead of just saying that the whole package goes to a specific file, they have like two variations. One's for import, which is the MJS, and one for require, which is the CJS. So let's try to do that and see what happens. Cool. So we can have those exports added. And then the second thing we need to do, we need to, let's call it, create yeah, I guess the easiest way would be to just write a small script that would create these two package JSON files. Let's call it it's probably some package that does that, but let's create a build tools and create or dist package JSON.js, and then const fs require fs write file sync dir name const path require path. And I'm not using TypeScript here because it's super simple script, so I probably can get away. It's going to be just a few lines. So we have one inside. They're using a shell script, but I don't like using shell scripts because those won't work on Windows. So we are using npm. It's like JavaScript, so we can just write a script in JavaScript instead of a shell script. And then we are going to write there json.stringify and pass it this object. All right, I think that's good. And then we can do the same, the ESM one and ESM, and then we can tell package JSON just run node build scripts, not build tools. I think that would be a better name. Dist package JSON build scripts. Okay, let's just run this and see if it does what it should do. Pass is not a function. Didn't I import it? The pass require pass. I think I did. Oh, pass.join, right? Join. Yeah, that's one of the problems when you don't use TypeScript. Luckily, this is a very simple script, so there is not too much that can go wrong. All right, so we have this CJS, and now we have a package JSON which says type CommonJS, and this one has a package JSON that says type ESM. All right, so now the release should probably be a bit better, or better. We'll find in a moment. Let's see if they also I think we should still include this main for like, I don't know if we should still include main. I have no idea, actually. Let's keep it because it's already there. Right, and then we can remove this one. So chore, how did we call it last time? Yeah, well, let's see. We already had exports in the past. Chore, hybrid npm module CJS plus ESM. Okay, all right, cool. Maybe that would work, maybe not. Let's release to npm and find out. First of all, I would probably want to, we haven't made any interesting changes, just run a different program. So we can ignore it, and then npx np to upload it to npm, the new version, and this is going to take a moment, and it will automatically do the release, and this release will already include some of our changes since the last release. Now one of the cool things about np is that it actually creates a changelog with all the changes since the last release. So we'll have that ready when we finish this release. And let's see if that works. Yeah, first of all, it tells us, hey, there are like all those new files since the previous release. Should we continue? I say yes. I would say this is a minor version because usually patch is when you fix a bug, and minor is when you add a new feature. But that's post 1.0. Anyway, new week, new version. I think that's fine. Cool. And yeah, let's wait for it to complete whatever it wants. It's going to run all the tests, make sure that everything passes, and publish it to npm so people can start using the new version with the semi-implemented timers and all of that cool shiny new stuff. Bumping, publishing, and now it should open a new window where we will create the release on GitHub. That should happen in a moment. Cool. So exactly 1 hour into this stream, we have 0 to 0. We added a skeleton of a timer, implemented CMP, added all this instruction, and also hybrid npm module. Okay, let's hope this is good. Publish release. And we are not going to test it now. I'll probably test it later because we have some more stuff to do. Or if any of you wants to npm install it and verify that it works. If it doesn't, we can keep iterating every week until we get it to work. In any case, this is still not ready for production really yet. But yeah, it's nice to keep track of the releases, of the changes in the releases. Anyway, I just noticed that we have both util and utils, and I don't like it. So what do you prefer? This is like plural, so let's just move this to utils and commit that. It can't be that this is the only file that changed, because somebody must have referenced this file. Fix or refactor util time to utils. There is a nice arrow here. Yeah, okay, cool. So we also did that. And now we can, just for the fun of it, npm start, yarn start, and this is the old hello uart, not the hello serial. We have so many variants of hello. Yeah, there are all those SAOs. Anyway, I think we had, so we don't need this anymore. Yeah, we had this like last time when we where we spoke about what we would need to implement, and there is like GPIO, timers, USB, PIO, all our this is our wish list, and I think yeah, we have a bit of timers, and in order to move forward with timers, we would also need interrupts. And I think that would be fun to work on right now. And then maybe we'll have some time to work on GPIO, and then we can try to figure out USB the next time. Or you know what? Yeah, let's do interrupts. All right, so interrupts. How does it work? How does it even work? So I went I went to the datasheet a few days ago just to find information about it, and there is information. Yeah, so there is like this, and we have this table of interrupts, and they are connected to the NVIC nested vector interrupt controller, and it has 32 inputs. There is 1 GPIO per core, so interesting. So core 0. Oh yeah, okay. So I guess both cores are interrupted by most of the peripherals, but for the GPIO, which is probably this PIO. No, PIO is PIO, so probably IO. Yeah, there is like 1 per CPU. That's what they say, but yeah, not sure. Maybe it's not configured here. Anyway, so there are only 26 RQ signals, and 26 to 31 are tied to 0, but the core can still be forced to enter interrupt handler by writing this to the IPSR register. Yep. All right. So there is a mask. Where is the mask? This is the mask. So each processor can mask different interrupt. These are like the registers that control that. Each of those registers, 1 bit for each, blah, blah, blah. And each core is system. And okay, so yeah, there isn't too much information here, but we now know each peripheral can like or for each peripheral there are like one of those interrupts. Timers have 4 different interrupts that they can produce. UART also has, each UART has 1 interrupt, and yeah, I think we will start by seeing so I guess firing an interrupt, meaning writing, setting those bits in the IPSR register, and then the CPU, the microcontroller, has to do something. And since I wasn't really familiar with how NVIC works, I Googled it and I found, it is not here, practical guide to ARM Cortex M exception handling, which explains about the NVIC, and there is like a lot of information here, but I'm not sure. Yeah, so we have all those like so this is like the exception table, the vector table, and you remember, or maybe not, that exception entry number 0 is the stack pointer, and then we have like the reset address, and then a bunch of exceptions, and then the M7 V7M good graphic with display exception number mapping. Let's see if it actually does. This is the V6, but maybe it also does exception, maybe NVIC. Yeah, does it have this? I don't see. Anyway, there is an algorithm here, so maybe it's external interrupt input behavior, edge, blah, 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 blah. No idea what they want from me. All right. That was it about the NVIC. So yeah, there is like a bunch of registers that control probably clearing interrupts, and yeah, interrupt set enable, interrupt clear enable, set pending, clear pending, and there is like priority registers. All right. So these are like the registers for the NVIC. STS, what's STS? Anyway, we would need to system control region, probably STS, status configuration, and then we have those registers, 1, 2, 3. So there is set and clear, set pending, clear pending, and I think one of those registers was mentioned here. IPSR, NVIC IPSR. So that's probably NVIC IPSR. So yeah, so I guess those registers just set and clear interrupts, and then those are probably to mask them, I guess. Is there? No, there is like proc0 and mi mask. So masking is, where is that? Proc0. That's inside the CCFG. System config registers, right? Let's see. So it's like one of the peripherals, is it? RP2040 CCFG. Yeah. So let's start by creating this CCFG peripheral. Let's new RP CCFG, or maybe RP2. I mean, I think, yeah, we call that one RP. Maybe we'll change it later, or yeah, I think in there, I saw somewhere in there like SDK that they call this whole family RP2. Actually, it's RP2040 CCFG. Just like, I don't know if they will ever release a different chip from this family. It will probably have different implementation anyway. So yeah, so CCFG, and then we can implement this peripheral in the peripherals directory, ccfg.ts, and let's just copy paste because I love copy pastes. RP2040 CCFG. I think it's more readable this way, more legible. Yeah, okay, and then we can implement this peripheral. So we don't need an byte, and then we can just, copy all the register information from the datasheet. So we have this const, this is at offset 0, and this one is at offset 4. And right now we only have one. We don't really implement multi-core operation. We'll probably get to that at some point as well. There is a way to, what else do we have here? We don't have too many registers here, so that's nice. That's nice. Yeah, probably most of them aren't even too relevant for us. But this one is interesting, the interrupt masking. So let's see. Let's have another variable in the RP2040 that will interrupt mask. Maybe we'll put it next to the IPSR because it's related to interrupts. Interrupt mask is, I think it's, if it's, what's the recent value of it? It's 0. Enable NMI. So okay, so it's 0 by default. Interrupt NMI mask. Cool, and then we can change this CCFG, so proc0 NMI mask, turn this dot RP2040 dot interrupt NMI mask, and then let's make it also writable. And I have no idea if I'm doing anything useful right now because I have no idea if this is actually used by the code, but it was mentioned in the data sheet, so maybe. So this .RE20. So now we have this new peripheral, and the next thing we probably want to do is to implement all those registers, like that was all those NVIC registers. Oh, there is like a description of them here as well. Nice. Yeah. So yeah, writing 0 has no effect. Writing 1 has enables interrupts, and reading just returns, I guess, the value of the. These are like interrupts enable and clear, and forces the interrupts into panning state. And how is it like? Is it like the same as the IPSR register of the core? There is like this IPSR register in the core, right? Or am I mixing things up? And there isn't. Oh, there is IPSR. Okay, not confusing at all. IPSR and IPSR. So what is IPSR? Oh, okay. So IPSR holds the exception number of the exception being processed. And IPSR is like the interrupt status, I guess. Yeah, not confusing at all. Okay, cool. So we have interrupt status and interrupt enable, and then there is like this interrupt priority. How does that work? So there are 7 of them, and then yeah, there is like a priority for, I guess that's like 2 bits for n. 2 bits, I guess, per. Yeah, it seems like the priority is 2 bits. Okay. Let's see if there is anything about that here. NVIC. Yeah, it's 2 bits. So 0 is the highest, and okay, this is the lowest. So okay, so first of all, let's create like stuff to hold these registers. How many registers do we have here anyway? Yeah, it's like everything that starts at E0000. So yeah, we can probably, it's not the peripheral per se, because it doesn't have like all those behaviors of a peripheral. And do we have like something that looks into these addresses? I think we have a bunch of hooks that go to these addresses. That's inside the system control block. There is like this VTOR that we have seen. We have used it, I think, the vector table offset register. Oh, there is also interrupt control and state register. Another one. Set pending non-maskable interrupt to set or clean. Okay. Another way to set interrupts. Okay, that's interesting. Anyways, yeah, they all seem to be in the same region. It's like under this priority. Yeah, so they all seem to be in the same region. That was 2 and power supplies 2.4 Cortex M0 NVIC list of registers. Yeah, so they're like, oh, this one was E00, but they all start like from 0E. That's the SCB probably. Cool. So let's make our life easier. Instead of having like those read hooks, we'll just do something like that. So instead of like this system control block, we can do something like yeah. So let's maybe we'll have a different class to take care of this. Yeah, let's write it here and then refactor. Okay, so this dot write hooks set and then system control block plus so we have this IPSR, right? So whenever somebody writes to it, then let's define the constants. So this is here. Yeah, let's stay consistent with the datasheet offset. So where is this VTOR anyway? Yeah, so let's say that instead of calling this system control block, let's call it PPB base, and it will be equal to this, and then we can have offsets relative to this. So we can probably copy this table, or maybe just copy the specific entries. So this is VTOR, and we have like we don't care about those, I guess. This is tick at the moment. It's like a built-in timer of the our Cortex core. Cool. So NVIC IS. Can I just copy all of those? Yes. And then we can. Right. So const offset this equals this. Maybe we'll keep that as a comment for now. Cool. And then now we can just write code that will and that's no longer system control log, that's pp base. Okay, and then offset. And we are probably going to refactor it very soon, but for now, whenever we write address new value, then we set this dot pending interrupts is just we bitwise OR it with the new value, because that's what the datasheet said for IPSR. If we write F0, there is no effect, but if we write 1, there is interrupt state to pending. So let's create a new pending interrupts property. Where was that created? I hate when it creates it randomly. Yeah, let's put it together with the other interrupts. So pending interrupts, and it starts with, starts with 0, and also we have like I think the another variable for the enabled interrupts, and then we just need to wire those. So okay, so there is like IPSR, ICPR, right? ICPR is like clear pending, so we are just clearing the pending, and then we have the enable ones, ISCR, which is just set DNA. Oh, there is a name for this register, setDNA. What happens with this setDNA? Does it appear anywhere else? Interrupt set enable. Yeah, I think the only way to access it is using this. So yeah, so we can call it enable interrupts or whatever we enable interrupts. And what was the name of this register? ISER. Set enable register. So just bitwise or to enable the interrupt, and probably ICER to clear it. All right, so we implemented those registers, and now let's just create the read hooks for them. So with the read hooks, it's even easier. We don't get a new value. And then, if I'm not mistaken, we should just return the current value. If I read that correctly, we don't need the address here anyway. We can even make it shorter if we remove this and just return the value. Yep. Okay. Let's just double check that both the reading from the without the offsets, reading from both of them returns the set DNA, read interrupt disabled, interrupt disabled. Yeah, it seems like they return the same thing. Cool. So now we have like a way to enable and disable interrupts from, like, the code can enable and disable interrupts and change the list of pending interrupts. And then let's also implement interrupt priority. There was like this list of interrupt priorities. Where was that? So we implemented all these. IPR. Use the interrupt priority registers to assign 0 to 3. 0 is the highest. So yeah, so it seems like a pretty straightforward read-write registers. All right, so let's just, and there are like 7 of those, right? Where are you? List of registers, yeah. From 0 to 7, from 0 to 8, not inclusive, and then we can set this right hook and read hook. And we can probably have think yeah, I think a very interesting way to store this would be to actually use store it in a different way. So we can have like priorities per level, so like an array of 4 numbers that what's the default? I guess the default is everything is priority 0, so it's the highest priority, right? Yep. Cool. So yeah, everything is 0 by default, so let's have interrupt priority, and that would just that would just make our life really easier when we go to implement like the interrupting mechanism. It will also be probably faster. So basically the index of this array will be like the mask of all of the interrupts that sit at this priority level. So there are like 4 priority levels, so we have like 4 numbers, and initially all the interrupts are priority 0, so they sit at location 0. And then when we write read to this, that was offset NVIC priority 0 plus I, then we just need to change those levels. So for instance, yeah, we just need the new value, and then I is actually the index of the register, so const I, const interrupt index is actually we have like 4 interrupts in each register, so there is like from each byte the highest the highest 2 bits are like the priority. So let's maybe we'll change I just to make it reg index. So the index of the register for byte index, the index of the byte index. So go over each of the bytes, and then const interrupt number is just reg index times 4 plus byte index. So basically mapping from the byte index to the number of interrupt. Const interrupt priority, we need to extract the byte from the new value, so shifted by 8 times byte index. And after we do this shift, so let's say we have like the lowest byte, or doesn't matter, we need to get just the top 2 bits, so we would also need to shift it to add 6 to the shift, so to get those bits, those 2 highest bits. And don't worry, we are going to write some code to test this, because there is no chance it's going to work on the first time. And then we can, so we know the interrupt maybe number, and now we can just clear this interrupt in all the levels. Did we call it level or priority? Const priority, or let priority runs from 0, priority goes to this dot interrupt priorities dot lengths priority plus plus, and this dot interrupt priorities at priority. We are just removing this interrupt from all the priorities, and then only setting it. What did just happen? Okay, so clear this bit, and then just setting it. We don't need this. So at the specific, maybe we'll change it to new priority. So set this bit at a new priority. Actually, I'm not sure why they haven't implemented it. Oh, I don't know. I think that like storing priorities like that makes more sense when you need to go over priorities and find all the interrupts of a specific priority. But who knows? I don't know why they did that this way. Anyway, let's implement also the read hook for each of those registers. So the read hook is going to be pretty interesting. We don't care about a new value, and let result equals 0. And then for each interrupt, we need to find its priority. So there are a few ways to go about it. I will just do, so we have the interrupt number, and then if I will just search for its priority. So if this interrupt is on, then our result equals priority, and then we need to do the opposite of what we did here. Basically shift it left by 8 times byte index plus 6. So move it to the right position in the result array, and then we can return result. And I literally have no idea what I just did here, but let's write some code to test it and see if we got the interrupt priorities right. Okay, so let's add another piece of, we don't need, I mean, this works. Describe NVIC registers, and then we can write a few test cases just to see that everything works, or maybe not. Cool. So first of all, let's see. So writing to yeah, let's start with a simpler test. So there was like this yeah, IPSR should corresponding interrupt bits. So let's assume that we have RB2040 dot pending interrupts. Let's say that we had only the lowest interrupt, like number 0 pending, and then we write don't need this one, we write to this, it's the offset of this, so we write here the value 10 hexa. So basically we know it should enable it, so we should have like maybe right here 16 makes more sense, 32. We should have the result pending interrupts. Yeah, it should be just like, you know, bitwise OR, basically. Just enable this interrupt. And it doesn't work because of, let's see why. We don't need this, and 2040 and focus, and let's see if it got into the read hook we just added. Maybe, yeah. I'm starting to feel this whole code is going to move to its own class soon. Yeah, so right hooks, and the right hooks isn't executed because we got something wrong. I think the address is correct. Wait a second. I think we wrote to the wrong register. We want set pending, not clear pending. So that's at 200, right? Yep. Okay, it's green. Perfect. This is passing, and then I think the ICPR. Now we want to write to IPSR, so that's 280. And let's say we have like FF. Then if we clear this one, it should be EF should clear. Let's remove this from test filter. Cool. So this one also works. And then let's have the same one with the ISER, ER, and ICER. Basically, it's the same, but just for, instead of pending, enabled interrupts, and then the addresses are different, 100 and 180, 180. Okay, cool. And then let's just reading from ISER should just return the value of the enabled interrupt. So we expect, actually both of them, we can do 2 in 1. So IS or IE should return. Oh, I have a typo in corresponding and no one told me corresponding. Okay. Maybe interrupt pending or pending interrupt bits, pending and enabled interrupt bits, enabled interrupt bits. Cool. And then reading from NVIC ICER should return the current enable interrupt bits. Okay, so reading radio int from here should equal this value. Okay, and then the same goes, oh, we want to check the second register as well. And then same goes for ISPR and ICPR. So basically that would 200, 280, and that should be pending interrupts. And let's say 2, just to make it less boring. Okay, so that was the boring tests. Now let's do some more interesting tests. So it should update the interrupt levels when correctly when writing to let's say NVIC IPR3. Now we'll just do this what the datasheet says. So yeah, so let's see. NVIC IPR3 is 40C. Hey Carlos, by the way, thanks for the message in the chat. Okay, so let's say we want to write the priority of interrupt 14 and set it to 2. So that would be let's see, 0 0 0 0 0 0 0 0, and interrupt 40 is in bit 22 23, so that's like yeah, this byte, and we want to set it to 2 or 3. Let's say we want to set it to 2. So we need to set the highest bit, so that would be 80 hexa to set just the highest bit, so it would be 2, so bit 33. Cool. All right, and then at this point we would expect something like that. Expect RP2040 dot, and we said that's interrupt number 4. Let's actually write it down. Set the priority of interrupt number, not 4, 14 to 2. Okay, RP2040 dot intra priority, priorities at 2 to equal, and then it should have bit number 14 set if everything works, and it doesn't. Let's see why, but before that let's also assert that priority 1 has no interrupts and priority 3 has no interrupts, and we should also assert that priority 0 has all the bits other than this bit set. And I think it will probably already blow up here. So yeah, so first of all, yeah, let's make it hexadecimal. That would probably, or yeah, let's do it hexadecimal. Otherwise, okay, so bit number 14, that would be bit, this is bit number 4, I think 14, or 14, 15, yeah, I think this is bit number 40. Yeah, but oh, it should be all the bits other than 40, so it should clear that bit. Okay, so I think that would be f minus 4 is A. Okay, that's, I think it's not doing anything. Let's see. I think I know why, actually. I think I know why. Oh, we are adding reg index, but I think we should multiply it by 4 because these are yeah, maybe we can do it like that. We can make them an array, so it will just index this array. I think that would be a bit more readable. So comma, Then we can just remove all those comments and say these are the interrupt priority registers. And yeah, let's call it IPRN, and then we can use this at regindex and at regindex, and this should probably fix the bug. Yeah, we can see now it, let's focus on this test, it gets into this function. So maybe we now, oh, interesting. So yeah, so we could, the result here is, this is the problem, that the result here is signed. So let's just, make sure the result is always signed when we compare, because we don't really care about whether it's signed or unsigned for now. All right, so now it should set this bit, or clear, we said this is interrupt number 14 at this register. Yeah, so this should have been interrupt number 14. Oh, yeah, it should be true because it's little Indian. I'm talking nonsense. It's not a data view. All right, let's see if the other one's probably not correct. Yeah, let's see what's going on here. So we have, let's see which interrupt numbers we are looking at. So yeah, these are not like the, oh yeah, these are the correct ones. So and then the new priority for each one. Let's see if we decode the priority correctly. Ooh, interesting. 2 interrupts are getting priority of 3. I don't think that's what we wanted to do. How comes? How do we calculate a new priority? We take the new value and shift it by, what does that give? So it gives, let's do unsigned shift. Something doesn't make a lot of sense to me. 16. Huh? Yeah, I think we had made that error. It's address and new value. Yeah, okay, now it passes. Cool. We already had that error in the past. I think the API for right hooks is bad. Let's fix that, because this is the second time we make this mistake. So probably it would make more sense to change how it works. There. Yeah, I see we also have this bug. There is probably a nasty bug. Yeah, we will probably have this same bug here where we look at value, but it looks at the address. There is a to do here. Yeah, let's just change this thing so the API doesn't take look at the address, and now everything will go. So yeah, I will look for all the right hooks in a moment to see if we haven't missed anything, but let's change the implementation of right hooks. Yeah, the place where we call right hooks to send the address as the second value. Nobody cares about it anyway. And now this is all green, and there is like that to do about a nasty bug that is probably irrelevant. Let's just run the program and see if we destroyed anything. Oh well, we did. We'll have a look at that in a moment to see. Oh wait, right hooks. Yeah, so value, new value, new value, new value, new value, new value. new value, and I guess this is the problem here. Let's console log the value. This, I mean, this had probably some kind of bug. And let's print dr0. We probably need to set it to 0 and not to 1 or something like that. And that would probably fix this strange bug. Maybe? Yep. Okay. Yeah, not sure why it worked, but anyway, now we fixed the API for the right hook, so it should be better. All right, so at this point we have, like, I think the basic stuff we need for like implementing interrupts. Let's just quickly check that the reading of interrupt level works. I don't think it's super important, but let's just check it anyway. So where was that? RP2040. That was, yeah, the spec, of course. So we can now actually, yeah, we can just, you know, add another assertion, accept RP2040.read uint 32, and then just read this value and assert that it's equal to what we have just set it to. And that's green. Note, that's not green because we are missing a 0. No, that's not green, probably because, yeah, we were missing a 0, but there is a bug hiding probably. Okay, let's try to see what this bug is. Where is this bug coming from? Why isn't it returning the wrong? Why is it returning the wrong value? Okay, console log interrupt number, and we expect that to go from 12 to 15, I think. Yep. And then let's print for each interrupt the priority that it finds. 12.0, 12.1, 2. Oh, why is this? Oh yeah, it should have been bitwise end to check if this bit is set. So now it would probably find only one priority for each interrupt. Yep, the priority is correct, but it still doesn't pass because we need to bitwise OR it into the result, and it passes. And yeah, probably this method works well as well. Let's just do a quick check. Should return the correct interrupt levels, interrupt priority level, right? Interrupt priorities when reading from, let's say, we'll take 5 in this case, and then we can just, you know, set the interrupt priorities, 2040.interrupt priorities. And let's say none of the interrupts are in level 0. And so this is like NVIC IPR5. Which interrupts does it control? 20 to 23. So we don't care about the rest. So let's say that interrupts at level 1 are 20. So that would be all zeros, but then, yeah, too many zeros? No, that's the correct. But then bit 20, so 16, 20 should be this one. Bit 20 is high, and also 21 is high. And let's say, yeah, we can say all the rest of the interrupts are in this level. And then interrupt level 2, let's say that, so we want, so we set 20 and 21, then we want 22. Or yeah, that's 22 to be at this level. And then we have 23, so we want all the rest of the interrupt. So that's F minus 3, that's C, I guess, to be in level 3. And then when I have no idea what I'm doing here, but when we are reading, we expect the first interrupt, the first two, like 20 and 21, to be in level 1, so that would be 40. Then the next one to be in level 2, that would be 80, and then C0. And it's not green. Let's see, what did I miss here or here? Let's do again this console log of interrupt number and priority, and see what's going on here. If so, yeah, everything is in priority 1. Oh yeah, I'm reading from the wrong register. This is 414 IPR5. Still not green. Let's see why. Let's focus on this test. So yeah, I probably, yeah, off by 1 error. Actually I said yeah, that's correct. I set the first one to level 1, then the next two ones to level 2, and the next one to level 3, and yeah, next, yeah, it's all shifted by 1, so the next, these are level 3. Okay, so it's still not correct because I guess of signs. Yeah, so let's just convert this to unsigned, and it passes. Great, cool. So yeah, so let's just interrupts, that's 0 to 20, interrupt 21, and this is interrupt 22 to 31, the remaining ones. Cool. So we have tests for this, and I think we have everything we need to implement, finally implement interrupts. Cool. So implementing interrupts. So whenever we whenever any of those values change, like the enables interrupt or pending interrupts, we should probably have a boolean that says that interrupts updated. So the microcontroller will know to check for them before executing the next instruction, and then these dot interrupts updated equals true. When we remove a pending interrupt, that probably doesn't matter, but and also when we disable, that's disable interrupt, right? One is interrupt enable. So when we enable an interrupt, it might matter. When we disable one, it doesn't matter. And when we change the priorities, I think we may need to reevaluate the interrupts in this case. So yeah, if we are writing, let's reevaluate the interrupts. And then we can do something like this. When we execute an instruction, if this dot interrupts updated, then this dot check for interrupts. And maybe we'll do it before reading the opcode, because we may move to different opcode. And let's see how we check for interrupts. So in order to check for interrupts, first of all, let's see if we have interrupt set is just this dot pending interrupts and this dot enable interrupt. So just the current set of interrupts that are enabled. And then I think we need to yeah, we need to do something. What do we need to do with that? We have this set DNA. Maybe the datasheet doesn't explain. Yeah. priority. I think the word priority will be useful here. Yeah, so each exception, yeah, that's how exception works. Is accepted, reset, blah blah blah, interrupt, fault, interrupts are secure, asynchronous, exception priority, exception, vector, inactive memory, active and pending, prime mask, all right. Okay, that's not very helpful, but we have this practical guide. There is this vect pending. What is vect pending? Ooh, we need to do this. Maybe? Do we have vect pending in this? That's not. Yeah, we have this vect pending and vect active, which is probably the currently active interrupt. Exception number is probably the interrupt. IPSR, yeah, probably the what's running right now. Anyway, so I think they said 0 is the highest priority, right? Yeah. So we need to just go I equals 0. I add these priorities dot lengths. Let's call it just priority. And then now that we have like this bit mask for each priority, we can just check which interrupts are, let's call it level interrupts, are enabled in this for this priority from the interrupt set that we just got, and this dot interrupt priorities. I don't know if we need a priority. Anyway, add priority, and then if there is any level interrupts, then we can just fire those interrupts. So we know we need to fire one of them, and we are just going to take the first. So maybe there is a better way, but let's just for I1 interrupt number is 1, is 0, interrupt number 32, interrupt number plus plus. And then we can do this dot interrupt this dot if level interrupt, and if this is this bit is set, interrupt number. If this is set, then we need to fire this interrupt. So this dot IPSR, the current I think IPSR is the current exception number, right? Then exception number. Exception IPSR. Oh, that's nice. You can't write to IPSR, you can only read it from it. Interesting, I didn't know that. Thread mode and learn. The currently executing exception number definition, and then, oh, that's the table from this guide. Cool. So yeah, so 16 plus the interrupt number. So 16 plus interrupt number. Cool. And then I guess we need to also change PC to go to this dot. We need to read unit 32. So we need to read this vector, this dot. So first of all, effect, right? The vector table. We read it from this vector, VICTR. How did we call that register? VTOR, yeah, VTOR. Yeah, so we need to read this VTOR register probably to find the vector table, and then relative to that we can find the actual interrupt handler index. So we have this offset VTOR and PPP base. So that was, where were we? This is getting gigantic. Cool. So yeah. So vector table this.readUint32 this.ppp. No, just ppp paste plus offset VTOR, and then we can read this from vector table plus or maybe we can have a different function, raise exception. That's how did we call that? Exception number. Yeah, exception number. Okay, raise exception. So this will just be the logic here. So then we just raise exception 16 plus interrupt number, and we also return because we don't want to raise too many exceptions at once, just for the first interrupt that we found. So that's setting IPSR to exception number, and then we go to exception number. And I'm not sure if we should do anything else at this point. Let's see, there is probably some pseudocode that assigns some value to IPSR. Yeah, execution priority. Interesting. So yeah, there is like a different exception priority. There is like this function that returns the exception priority with highest priority is 4, I2 to 47 if exception active is 1, and exception priority is less than highest pri, which is basically 4. So obviously it will be less than 4. Highest pri. Oh, highest pri is actually the smallest one. Yeah, so interesting. It seems to go from the end to the beginning. If primask.pm is 1, then boosted pri is 0. What is boosted pri? Boosted pri is less than, so basically taking the minimum. Okay, so this is basically finding the first highest pri is actually the minimum. So if I'm understanding correctly, it just like takes it goes over the list of pending exceptions or interrupt in this case, and takes the first one that has the highest priority. So that's, I think, what we did. And then we have, oh, there is like negative. So yeah, for interrupts, there is like, okay, this is probably what we did to find, and then NVIC. What is this times 8. Oh, this is taking the 2 bits. Okay, so basically those exceptions have higher priorities. So at some point we should probably take care of this as well when we are, when we have other exceptions to do when we implement the rest of the exceptions. So I think this just means that we can check for those before we check for interrupts. We also check if we had one of those exceptions and then raise them. Otherwise, keep with it checking for interrupts, and for those we'll get there. Don't worry. Okay, cool. And then okay, so we know how is probably ExceptionEntry behavior. This is what I was looking for. Okay, so ExceptionEntry. Okay, what does it do? On preemption of the instruction stream, the hardware saves context onto the stack pointed by one of the SP registers. The stack used depends. The stack context. APCS. No idea what is that. APCS. No idea what's that. ARMv6. Descending stack. Pushing counter. The hardware decrements before when popping. When pushing context to the stack, the hardware save 8 32-bit words, IPSR return address, LR, blah 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 blah. Okay. So push stack and exception taken. What does push stack do? Yeah, I think we can just copy this code and then figure it out. Oh, there is a bunch of stuff we need to do. Okay, let's do that. Cool. So before we do these changes, let's see. So there is like SP process or SP, and then we need to read one of the stack pointers and write, don't need that, not that. Oh, interesting. Why do we write those values to link register? No idea. Anyway, yeah. So how do we know control SP cell equals 1? Current mode thread. So let's start with assuming that we have this frame PTR for now. Let frame PTR equals 0, but we'll fix it in a moment. And then we can just this.write uint32 to the frame PTR address, and we don't really need to specify the size of the write. So we're going to write this.registers 0, this.registers. Okay, so we are writing it to some imaginary stack, which we don't really know at the moment. It's either SP processed or SP main. We'll read it in a moment. This.lr. Okay, and then we need to write here the return address, so that's probably this.pc. We'll comment it out, and then what is that? This one, what was that? Oh, we write the value of ExecutionPriority. I don't know what is this frame PTR line. Do we have it? Yeah, it's saved to one of the bits in ExecutionPriority. Bit number 2 in the SP. Why do we need that? No idea. Okay. Let XPSR, but let's do it anyway. So XPSR is this.xpsr, and we need to remove this. That's bit number 9. So this one, or VTOR align, and we need to put it at position 9. Okay, so we can just write this whole new value. Okay, cool. So again, I have no idea what I'm doing, just copying the datasheet and hoping this will work and will have exceptions and interrupts for the next session. All right, and then there is like this SP cell which probably selects the stack. What are these magic numbers? Okay, so what is this control SP cell? Do we have this? And what is this current mode? So we need this frame PTR. So let's, if this, then this, and this, else. Okay, let's define those values. Frame PTR, let be. Yeah, those are, and let frame PTR align. Okay, so now we need to figure out those pieces and then the SP process and the SP main, which I remember we encountered. And then again, so if we have this, then this.lr equals this magic value, else. Yeah, we need to find out this SP cell thing. This.lr else this.lr. Okay, I think we did half of this exception handler. Yeah, no, then this is not Pascal, this is JavaScript. Okay, and we don't need those bit size specifiers. And let's change it to 0. And this is 1. I just want the code to yeah. Okay, I just want the code to be valid so I can format it. This is like not 0b100, and the same here, not 0b100, and this is still not and 1. We can just take this, so 1, otherwise 0. So bit number 2. Okay, yeah, now the code formats, it still doesn't compile. So that was take something. That was push stack. And then we have the second one, which is exception taken. I hope this one will be easier. So yeah, so first of all, the values of these registers are just unknown, so we don't really care about it. Then we need to set a few values, and this one looks a bit easier. We don't need this. Yeah, I guess this means that WFE will return after this once we implement it. No idea what is this, so let's to do. Probably not very interesting. Yeah, I need to see what's this exception active. This is unchanged. We don't care. We need to switch to the SP main, and then I think we already have this logic where IPSR equals the exception number, and this is basically, I guess, writing this value to the PC, and this is vector table times 4 times, yeah, exception number. Yeah, good catch. Datasheet. And what is that? Vector table. Oh, reading from VTOR. That's what we do here. Cool. Okay, so and this is, we said this is like this. So yeah, so we have a few things we need to figure out, like those different stack pointers. I don't think we currently save them anywhere. There's like and I need to figure out what is this current mode. I mean, we read it and write it. So let's see what is current mode. Where is the current mode stored? What is this spatial register? Or God knows what. So what is current mode? You just say current mode, but is that like just a hidden register? I guess it is. Let's see. Probably. We have the control register. I mean, there gotta be some. There is like mode thread and mode handler, but where are those defined? Okay, there is like this enum. Oh, nice. There is a list of all the registers. So we have SP main, SP process, and then I guess, yeah, you see register number 13 is one of those, depending on which SP we are currently looking at, and all those. Okay, where is this current mode? First of all, it's an enum, so I guess this is 0 and this is 1. So let's add this knowledge to our code. This is 0. Let's just remove the, oh, we don't need const equals 1. Okay, and then maybe we can just define it as an enum. Execution mode is, yeah, I mean, there are enums, so why not use this? And I guess the default execution mode is thread. Here it is. No. Yeah, I don't see where they define this current mode, so if you have any information about where what's the default value of current mode, that would be useful, but I guess yeah, it should be thread. Yeah. Oh, we should probably also implement exception return. Probably there is an interrupt instruction that calls it. Or oh yeah, when we use bx, then there is like this. Maybe we'll add a node here. So we won't get to it this week, but let's add a node to do it next week. Current mode. So yeah, let's add a current mode variable. So another one. current mode, and the default is thread, right? I think so. Thread. I hope so. We'll figure out if it's incorrect. All right, and now go down here, and this dot current mode thread, execution mode thread. Okay, then execution mode dot handler, and this dot current mode equals. Okay, so we still have like this control register. What is exception active? Okay, conceptual array. Okay, what does it mean that it's conceptual? Okay, I guess we'll get there at some point. Yeah, we would need it to yeah, we'd probably need this, or maybe we don't. Do we need this nested activation somewhere? Unpredictable. Yeah, it's conceptual. Oh, we don't probably need this, so we can get rid of this. What is this doing? Okay. Okay. Probably nothing interesting from our point of view. What is this doing? Set event register. Sudo sets the processor, clear, turns true. Yeah, probably WFE. It will wake up from WFE. I don't know if we need it right now. So basically we need to take care of this stack selection and implement those multiple stack pointers, and also implement this return for exception return thing, and then, you know, just hope it works or start testing it and seeing what we got, like what bugs we got, and then fixing them. But I think we made a pretty good progress today. Released a new, untested, but a new updated version to npm, and spent 1 hour or 1 hour and a half taming interrupts. And I think we are pretty close to getting interrupts and maybe then exceptions. I don't know if we need one of those for the Pi Pico, but we will probably need at least the exceptions, the interrupts for the timers. And when we get to USB, we'll probably need that as well, and for the GPIO. So I think next time we'll probably finish with these interrupts, get them to work, figure out those two different stack pointers and what to do with them. And then probably start looking at GPIO, and maybe also playing a bit with the new RP2040 core or Pi Pico core for the Arduino, and seeing if we can get Blink to work. So take care of finishing those two items. And I don't know, it will probably take as usual more than anticipated, but I'm really looking forward to get to the USB, and then we can probably try running MicroPython or CircuitPython and see how that goes. So anyway, if you I'm going to commit this because we are out of time today. So that would be partial interrupt implementation. Still does code still doesn't compile since we are missing a few bits, but we'll do them next week. Also pay attention to that was, I think, in this bx instruction, exception return calls it to this excerpt of bxwrite PC. Cool. Oh, I need to stage my changes. Maybe we'll call it NVIC. That would be a new component. Maybe next time we'll refactor this to be live in its own class, or at least some of it. We'll see about that. Anyway, let's have this committed and pushed. And you know, if you feel like looking and figuring out this thing with the two different stack and this control, then cool, open an issue on GitHub or ping me on Discord, and I would love to look into that. Or if not, we can just do it next week when we get interrupts to work. I'm very optimistic that we'll manage to do it. And hi Steve, thanks for the hi on the chat. So until that, have a great week, and see you again next week. Bye bye.